An air bubble of volume 1 centimeter cube rises from the bottom of a lake 40 meters deep at a temperature of 12 degrees Celsius. To what volume does it grow when it reaches the surface, which is at a temperature of 35 degrees Celsius? The options given are 10.6 into 10 raised to minus 6 meter cube, 5.3 into 10 raised to minus 6 meter cube, 2.8 into 10 raised to minus 6 meter cube, and 15.6 into 10 raised to minus 6 meter cube. Now, let's look at this situation here. Suppose this is the surface of the lake and there's a water bubble or air bubble over here, which is at the bottom. So let these conditions be P1, V1 and T1, and at the surface the bubble rises, so let these two P2, V2 and T2. So the distance or the depth of the lake is 40 meters. Okay, so in order to find out the volume, we would use the equation P1 V1 upon T1 equals P2 V2 upon T2. However, in this V2 as well as P1 are unknown, so let's find out P1 first. So P1 can be found out by using P1 equals P2 plus the excess pressure due to the water height of the lake. So that can be given P2 plus H rho G, where H is the height of the lake or the depth of the lake, rho is the density of water, and G is the gravity, acceleration due to gravity. So therefore P2 is the pressure at the surface of the lake, which is nothing but atmospheric pressure. So that is 1.013 into 10 raised to 5 pascals, plus H is 40 meters, to rho, the density of water is 1000 kg per meter cube, and acceleration due to gravity is 9.8. So this, when we solve this, so it comes out to around 49 pascals. So this is the pressure at this point at the bottom of the lake. So now let's substitute the value of P1 in this expression. So we get the value as V2, or the volume over here, is equals to P1 V1 times T2 upon T1 times P2. Now since they have given that pressure, let's substitute these values. So 49 3300 times V1, or the volume at the bottom of the lake, is given as 1 centimeter cube. So to convert into meter cube, it would be 10 raised to minus 6 meter cube, upon the temperature T1 is given as 12 degrees Celsius. So when we add 275 to it and make it as Kelvin, so we get the value of 285 Kelvin, times P2, or the pressure at the surface, is 1.013 into 10 raised to 5 pascals, times this T2, temperature at the top surface, is given as 35 degrees Celsius. So converting it to Kelvin, we get as 308 Kelvin. So on solving this, we get the value as 5.26 into 10 raised to minus 26 meter cube. Now the approximate answer close to it is 5.3 into 10 raised to minus 6 meter cube. Hence option B is the correct answer. A gas at 300 Kelvin has pressure of 4 into 10 raised to minus 10 Newton per meter square. If Kb, that's the Boltzmann's constant, is given as 1.38 into 10 raised to minus 23 per Kelvin, the number of molecules per centimeter cube is of the order of, the options given are 10 raised to 3, 10 raised to 5, 10 raised to 6 and 10 raised to 9. Let's use the ideal gas relation PV equals nRT. We need to modify this equation a little. So let us multiply and divide the right hand side by Avogadro's number. So n times Avogadro's number into RT upon Avogadro's number. So R by Na is nothing but Boltzmann's constant. So N times the number Avogadro's number into Boltzmann's constant into T. So now the number of moles into Avogadro's number, that is number of molecules in each mole, this total term gives us the total number of molecules in the mixture or in the gas times Kb into T, so PV. So since they've asked the number of molecules per centimeter cube, so we need to divide by the volume. So P is equals to N upon V times Kb into T. So we need to find out this term N upon V, that is the number of molecules per centimeter cube. So therefore N upon V is nothing but P upon Kb times T. Now substituting the values, but however we need to know that this volume is generally due to all the units are given in MKS system, so volume would be in meter cube. So in order to convert into centimeter cube, because they've asked per centimeter cube, so we'll need to add a term of 10 raised to minus 6 here. So the answer that we would get would be in per centimeter cube. So now substituting the values, so we get 4 to 10 raised to minus 10, 10 raised to minus 6 upon kb is 1.38 into 10 raised to minus 23 into the temperature is given as 300 Kelvin. So this comes out to have an order of 10 raised to 5, hence option B is the correct answer. The diameter of an oxygen molecule is 3 angstrom. The ratio of molecular volume to the actual volume occupied by the oxygen gas at STP is, the options given are 2 into 10 raised to minus 4, 10 raised to minus 4, 1.5 into 10 raised to minus 4 and 4 into 10 raised to minus 4. Now the diameter is given as 3 angstrom, that is nothing but 3 into 10 raised to minus 10 meters. For the sake of solving, let's convert it into centimeters, so that is 3 into 10 raised to minus 8 centimeter. So this is the diameter, so therefore the radius that we would get is 1.5 into 10 raised to minus 8 centimeter. So this is the radius of oxygen molecule, and the molecular volume would be nothing but 4 upon 3 pi r cube. Here we are assuming that the molecule is a sphere, so 4 upon 3 pi r cube times n. N is nothing but the Avogadro's number. Here, why we are taking Avogadro's number is because since we don't, in order to compare, we would be taking a standard volume of 1 mole of gas. So 1 mole of gas occupies a volume of 22.4 liters, that is standard, and that is nothing but 22.4 into 10 raised to 3 centimeter cube. So since we would be calculating the volume of 1 mole of oxygen molecules, therefore we take Avogadro's number over here. So therefore this molecular volume comes out to be 4 by 3, pi is 3.14, radius we found it as 1.5 into 10 raised to minus 8 cube times Avogadro's number is 6.023 into 10 raised to 23 molecules. So this value comes out as 8.51 centimeter cube. So therefore the volume occupied by molecules in 1 mole of a gas is 8.51 centimeter cube. However, due to the movement of molecules, the volume occupied at STP 1 mole of any gas occupies a volume of 22.4 liters, that is nothing but 22,400 centimeter cube. So let's take a ratio of this. So V upon the STP volume would come out as 8.51 centimeter cube upon 22,400 centimeter cube. So this ratio is 4 into 10 raised to minus 4. It's approximately equal to 4 into 10 raised to minus 4. Hence, option D is the correct answer. 1/2 mole each of nitrogen, oxygen, and carbon dioxide are mixed in enclosure of volume 5 liters and temperature of 27 degrees Celsius. The pressure exerted by mixture is. The value of universal gas constant is given as 8.3 joules per mole per Kelvin. The options are 7.8 into 10 raised to 3 Newton per meter square, 5 into 10 raised to 5 Newton per meter square, 6 into 10 raised to 5 newtons per meter square, and 3 into 10 raised to 5 newtons per meter square. Here this is 7.8 into 10 raised to 5 newtons per meter square. So now, in order to solve this sum, we need to know that the Dalton's law of partial pressures. So this law basically says that the pressure exerted by the mixture is equal to the sum of the individual uh, constituents, or the pressure exerted by sum of individual constituents. So total pressure would be pressure exerted by nitrogen plus pressure exerted by oxygen plus pressure exerted by carbon dioxide. So therefore, using the ideal gas relation, PV equals nRT. So P can be written as nRT upon V. So substituting P for each of the molecules, so total pressure P would be nRT upon V for nitrogen plus nRT upon V for oxygen and nRT upon V for carbon dioxide. Now since the volume is constant, that is 5 liters, so all the volumes would have the same notation, and the temperature is also constant of 27 degrees Celsius. Therefore we don't need to mention specific temperatures for each of the molecules. So this can be written as 3 times nRT upon V. Now here the value of N is given as half mole, and therefore now just solving this, temperature is given as 27 degrees Celsius, so which is nothing but 300 Kelvin, and the volume is given as 5 liters, that is nothing but 5000 centimeter cube. In order to convert to meter cube, it would be 5 into 10 raised to minus 3 meter cube. So the value of pressure comes out as 3 into N is 8.31. This is the value of R, and T is 300, N is half, so half upon volume V is 5 into 10 raised to minus 3 meter cube. So solving this expression, we get 7.48 into 10 raised to 5 Newton per meter square. Now the closest value over here is option A, hence option A is the correct answer. Which of the following graphs represents the behavior of an ideal gas? Here they are given 4 graphs. Now, in order to solve this, let us look at the 3 laws, that is Boyle's law, Charles' law, and Gay-Lussac's law. So Boyle's law says that at constant temperature, P1 V1 is equals to P2 V2. So, and the Charles law says that V2 T2 is equals to V1 T1 at constant pressure, and Gay-Lussac's law gives that constant volume pressure is proportional to T, so therefore P1 T2 is equals to P2 T1. Over here also V2 T1 is equals to V1 T2. So therefore from this we can see that the volume and temperature graph in this at constant pressure, let's look at option A. So for constant pressure, volume and temperature is constant line of pressure line. So therefore option A is the correct answer because it follows Charles' law. Hence option A is correct. Pressure versus temperature graph of an ideal gas of equal number of moles of different volumes are plotted as shown in the figure. Choose the correct alternative. Now in this we have been given the pressure temperature graphs, and since as we can see that the PT graphs have straight lines and which pass through the origin, so therefore we can conclude that pressure is proportional to temperature from this graph. But from ideal gas equation we know that pressure is equals to nRT upon V. Now in this N and R are constants, so we can also say that pressure is inversely proportional to volume into temperature. So the slope of a line is nothing but y by x. So therefore pressure upon temperature is inversely proportional to volume, or that is also equal to the slope. So from this, the line which has a higher slope has a lower volume. As we can see, slope of this line 1 2 has a lowest, so slope of 1 2 is less as compared to slope of 3 4. So therefore slope of 1 2 is less as compared to slope 3 4, and therefore for a given slope, so we get V2 is greater than V3. Also for a given slope line, all the volumes are equal on that, all the volume of all the points are equal on that line. So therefore V1 equals V2 and V3 equals V4. So using these three relations that we get, so option C is the correct answer. Given is the graph between PV by T and P for 1 gram of oxygen gas at two different temperatures T1 and T2 as shown in the figure. Given density of oxygen is 1.427 gram per meter cube. The value of PV by T at the point A and the relation between T1 and T2 respectively are. The options given are 0.259 joule per Kelvin and T1 is less than T2. 8.314 gram joule per mole per Kelvin and T1 is greater than T2. 0.259 joule per Kelvin and T1 is greater than T2, and 4.28 gram joule per Kelvin and T1 is less than T2. Now let's look at the ideal gas relation. PV is equals to nRT. Here the N, or the number of moles, can be rewritten as PV is equals to mass of gas upon molecular weight times RT. So PV upon T, this when we get T on this side, so PV upon T is equals to M upon R. So for a given mass of gas, the relation of PV by T is constant because all these terms, that is the mass, molecular weight and universal gas constant, is a constant. So therefore PV by T for all values of pressure is constant. Hence we get this ideal gas line as a straight line. So now PV by T for oxygen in this case would be 1 gram of oxygen upon the molecular weight of oxygen O2, that is 32 grams per mole, and the R value is given as 8.31. So this value comes out to be around 0.259 joule per Kelvin. And as we can see, T1 is greater than T2. So both these answers come together in option C. Hence option C is the correct answer. From a certain apparatus, the diffusion rate of hydrogen has an average value of 28.7. The diffusion of another gas under the same conditions is measured to have an average rate of 7.2 centimeter cube per second. The gas is, the options given are nitrogen, helium, argon and oxygen. Now, in order to solve this, we need to know the Graham's law of diffusion. So, according to Graham's law of diffusion, so the rate of diffusion R is proportional to root of the density, or inverse, pardon me, the rate of diffusion is inversely proportional to the density. So therefore R2 upon R1 is equals to root of rho 1 upon rho 2. So now here R1 is nothing but rate of diffusion of hydrogen, that is 28.7, and R2 is rate of diffusion of the unknown gas that we need to find out, and that is 7.2 centimeter cube per second, and same here centimeter cube per second. And M1 is the molecular mass of hydrogen, that is 2. Now substituting these values, uh, by the way, this root of rho 1 upon rho 2, the densities can be specified in terms of molecular weights as m1 upon m2. So now in this, substituting the values, we get r1 upon r2 is equals to root of m2 upon m1. So 28.7 upon 7.2 is equals to root of m2, that is the mass of the unknown gas, upon 2, that is the molecular weight of hydrogen. So m2, by squaring it, we get 28.7 upon 7.2 squared times 2. So this value approximately comes around 32, and as we know 32 is the molecular weight of oxygen, so therefore the gas should be oxygen. When the temperature of gas filled in a closed vessel is increased by 1 degree Celsius, its pressure increases by 0.4%. The initial temperature of the gas was, the options given are 250 degrees Celsius, 25 degrees Celsius, 250 Kelvin and 25 Kelvin. Now let's use the ideal gas relation PV equals nRT. Now since volume of the vessel isn't changing, so volume is constant, nr are anyways constant, so therefore P2 upon P1 is equals to T2 upon T1, and we need to find out the value of initial value of temperature, so T1 is equals to T2 times P1 upon P2. Now since they have given that the temperature is increased by 1 degree Celsius, so T2 would be T1 plus 1. Now it doesn't make a difference whether we take it as degree Celsius or Kelvin, so the temperature difference is anyways 1. So here it is 1 times P1 was, let's say, 100. If P1 was 100%, so P2 would be 4% in 0.4% increase, so that is 100.4. So T1 plus 1 times 0.99. So T1, on solving this, we get as 250 Kelvin. The answer we got in Kelvin because all the units are in standard MKS form. So therefore we got in Kelvin. Hence option C is the correct answer. The equation of state for 5 gram of oxygen at a pressure P and temperature T when occupying a volume V will be, the options given are PV is equals to 5 by 32 RT, PV is equals to 5 RT, PV is equals to 5 by 2 RT, and PV is equal to 5 by 16 RT. Now let's look at equation for state. PV is equals to nRT. Now N over here is nothing but number of moles that can be given as mass of the gas upon molecular mass of the gas. So mass of the gas is given as 5 grams, and the molecular mass of oxygen, since oxygen is diatomic, it exists as O2. So therefore the molecular mass would be 32. So 5 upon 32 would be the value for N. Substituting the value of n in this, we get PV is equals to 5 by 32 times RT, and hence option A is the correct answer. The volume of water molecule is, take the density of water as 10 raised to 3 kg per meter cube and Avogadro's number as 6 into 10 raised to 3 per mole, 6 into 10 raised to 23 per mole. The options given are 3 into 10 raised to minus 28 meter cube, 3 into 10 raised to minus 29 meter cube, 1.5 into 10 raised to minus 28 meter cube, and 1.5 into 10 raised to minus 29 meter cube. So, as we know, the molecular mass of water is 18 grams, and therefore, uh, and since molecular mass of water is 18, and therefore the number of molecules, if we consider 1 mole or 18 grams of oxygen, that would be equal to Avogadro's number. So the number of molecules would be 6 into 10 raised to 23 molecules in 18 grams. So therefore, mass of each molecule. So mass of each molecule would be, the equal to 0.018, since this gram is converted to kg. So 0.018 upon the total number of molecules, so 6 into 10 raised to 23. So this comes out as 3 into 10 raised to minus 26. So this is the mass of each molecule, and therefore the volume can be given as mass upon density, so which is equals to, mass is 3 into 10 raised to minus 26 upon the density is given as 10 raised to 3. So therefore this value comes out as 3 into 10 raised to minus 29 meter cube, and hence option B is the correct answer. A vessel has 6 grams of oxygen at pressure P and temperature 400 Kelvin. A small hole is made in it so that oxygen leaks out. How much oxygen leaks out if the final pressure is P by 2 and the temperature is 300 Kelvin? The options given are 5 grams, 4 grams, 2 grams and 3 grams. Now let's look at the ideal gas relation. PV is equals to nRT. The number of moles can be written as mass of the gas upon molecular mass times RT. So for the first condition, it would be P1 V1 is equals to M1. The molecular weight wouldn't change, so it's constant. R is also constant, and T1 is given as 400 Kelvin. Similarly, for the second case, P1 P2 V2 is equals to M2 upon capital M times RT2. Now, since the volume of the vessel doesn't change, so V1 is equals to V2. Now, dividing these two equations, we get P1 upon P2 is equals to M1 upon M2 times T1 upon T2. Now we need to find out the value of M2 over here. So M2 is equals to M1 T1 P2 upon P1 times T2. Now P2 is given as P1 by 2. So M1 T1 P1 by 2 upon P1 times T2. So these gets cancelled. M1 is given as 6 grams. T1 is given as 400 Kelvin upon T2 is 300 Kelvin, and this 2. So the value of M2 comes out to be 4 grams. So therefore this is the final mass of final mass of oxygen left in the vessel. So therefore change, or the mass that has leaked out, would be delta M, that would be 6 minus 4, that is 2 grams. Hence option C is the correct answer. A sample of an ideal gas occupies a volume V at pressure P and absolute temperature T. The mass of each molecule is m. Then the density of gas is, the options given are mkt, pm upon kt, p upon m into k, and p upon kt. Now we need to know the ideal gas law. PV is equals to nRT. Now in this, the value of n, let's take it as 1 mole. So PV is equals to RT. Now this volume, as we know, density is equals to mass upon volume. So density is equals to mass upon volume. So the volume can be written as mass upon density. So therefore P times mass upon density is equals to RT, and we need to find out the density relation. Therefore rho is equals to Pm upon RT. In this, the value of universal gas constant is taken as K, so Pm upon Kt would be the answer. So that is option B. An ideal gas is compressed isothermally until its pressure is doubled and then allowed to expand adiabatically to regain its original volume. The value of gamma is given as 1.4 and 2 raised to minus 1.4 is given as 0.38. The ratio of final to initial pressure is, the options given are 0.76 is to 1, 1 is to 1, 0.66 is to 1, and 0.86 is to 1. So let V be the original volume. So let V be the original volume, and for isothermal process, temperature is constant, so therefore PV is equals to a constant. So for this process, initial and final, so initial pressure times initial volume would be equal to the intermediate, so let's call it P dash, intermediate pressure and intermediate volume. So the intermediate volume would be V initial times initial pressure upon the intermediate pressure. So that is equals to, let's take the initial volume as V, as we've specified here. So Pi upon the intermediate pressure, it says that the pressure is doubled, so it would become 2 times the initial pressure. So this comes out as V by 2. So the intermediate volume is half the initial volume. And now for adiabatic expansion, so for adiabatic process, PV raised to gamma is equals to a constant. So therefore, now this intermediate pressure, now this intermediate pressure becomes the initial pressure for expansion. So therefore, 2 times the intermediate pressure can be written as 2 times initial pressure times the intermediate volume is V by 2, or initial pressure upon 2 raised to gamma is equals to the final pressure now and the final volume raised to gamma. So therefore the ratio of PF, or the final volume or final pressure, to the initial pressure Pi can be given as 2 into 2 raised to gamma. Since this V and V are constant, so they get cancelled out. So 2 into 2 raised to gamma, so that is 2 into 2 raised to minus 1.4. So this value is 2 into 0.38, so that is nothing but 0.76. So PF upon PI is 0.76 is to 1, hence option A is the correct answer. An ideal gas at a pressure of atmosphere and temperature 27 degrees Celsius is compressed adiabatically until its pressure becomes 8 times the initial pressure. The final temperature is, given that the gamma is 3 upon 2, the options are 627 degrees Celsius, 527 degrees Celsius, 427 degrees Celsius, and 327 degrees Celsius. Now, here we have been given that the value of P2 is 8 times of P1, and the temperature T1 is given as 27 degrees Celsius, which is nothing but 300 Kelvin. For adiabatic process, PV raised to gamma is equals to a constant, and as we know PV equals nRT, so V can be proportional to T upon P since N and R are constants. Substituting this value of V over here, so P times T raised to gamma upon P raised to gamma is equals to a constant. So therefore P raised to 1 minus or gamma minus 1 into T raised to minus gamma is equals to constant. So this can be modified into this form. So now what we can write is P1 raised to gamma minus 1 to T1 raised to minus gamma is equals to P2 raised to gamma minus 1 times T2 raised to minus gamma. So therefore T2 upon T1 raised to minus gamma is equals to P1 upon P2 raised to gamma minus 1. So the value of T2 is equals to T1 times P2 upon P1 raised to gamma minus 1 upon gamma. So that is nothing but 300, that is T1, and P2 is 8 times P1, so P2 upon P1 would be 8. The value of gamma is given as 3 by 2, which is 1.5, so 1.5 minus 1 upon 1.5. So solving this expression, we get the value as 600 Kelvin. Now 600 Kelvin, to convert into degrees Celsius, we need to subtract it by 273 degrees. So the value comes out as 327 degrees Celsius. Hence option D is the correct answer. 0.014 kg of nitrogen is enclosed in a vessel at a temperature of 27 degrees Celsius. How much heat has to be transferred to the gas to double the RMS velocity of its molecules? The options given are 1200 Kelvin, 600 Kelvin, 300 Kelvin, and 150 Kelvin. In this question, the options are given in Kelvin and they've asked for heat. So probably we need to find out the temperature of the gas, final temperature. Now the expression for Vrms is given as root of 3RT upon M. Therefore, Vrms for the first condition upon Vrms for the second state is equals to root of T1 upon T2, since R and M are constants. Now, as we know that Vrms, or the second condition, the RMS velocity is doubled, so Vrms for the first would be 2 times Vrms again for the first. The Vr2 can be written as 2 times. So upon T1 is 300 Kelvin, upon T2 is what we need to find out. So squaring this, we get 1 by 4 is equals to 300 upon T2. So therefore T2 is 300 times 4, that is equals to 1200 Kelvin. Hence option A is the correct answer. 1 kg of diatomic gas is at a pressure of 8 into 10 raised to 4 Newton per meter square. The density of the gas is 4 kg per meter cube. The density of the gas due to its thermal motion is, the options given are 3 into 10 raised to 4 joules, 5 into 10 raised to 4 joules, 6 into 10 raised to 4 joules, and 7 into 10 raised to 4 joules. So now the formula for internal energy can be given as F upon 2 times N kb into T. Now since the diatomic gas is given, so the degrees of freedom F for diatomic gas is 5. So 5 by 2 N Kb times T. Also, uh, from ideal gas relation, PV is equals to nRT, and this nRT can be modified to be PV is equals to N times Kb into T. And therefore, from these two equations, we can equate them to such as PV is equals to 5 by 2 times PV is equals to U. So this is the internal energy. So U would be equals to 5 by 2 times the pressure is given as 8 into 10 raised to 4, and the volume is given as 1 by 4. Since the density is given as 4 kg per meter cube, so the volume is nothing but mass upon density, and mass is given as per meter cube, so we can write as 1 by 4. So therefore U, this value comes out as 5 into 10 raised to 4 joules. Hence option B is the correct answer. The kinetic energy of 1 gram of molecule of a gas at normal temperature and pressure is, the options given are 0.56 into 10 raised to 4 joules, 2.7 into 10 raised to 2 joules, 1.3 into 10 raised to 2 joules, and 3.4 into 10 raised to 3 joules. Now, the kinetic energy for 1 gram is given by 3 upon 2 times RT. Now substituting the values, 3 upon 2, the value of R is 8.31, and for normal temperature and pressure, the value of T is 0 degrees Celsius or 273 Kelvin. Now solving this expression, we get the value of kinetic energy as 3.4 into 10 raised to 3 joules. So that is nothing but option number D. A gas is filled in a container at pressure P0. If the mass of the molecules is halved and the RMS speed is doubled, then the resultant pressure would be, the options given are 2 times P0, 4 times P0, P0 by 4, and P0 by 2. So as we know, the value of expression for pressure can be written as 1 by 3 rho c square, where c is the RMS speed and rho is the density. So we can write this density as mass upon volume times c square. So since the container isn't changed, so volume remains constant, so we can say pressure is proportional to mc square. So P2 upon P1 is equals to M2 C2 square upon M1 C1 square. Now they have given that the mass is half, so M2 would be M1 by 2, so times M1 into the RMS speeds are doubled, so C2 would be C1 times 2 times C1 upon C1 squared, so P2 upon P1. So therefore P2 upon P1 is equals to 1 by 2 times 4C1 squared upon C1 squared. So this would get cancelled and this would get cancelled as 2. So P2 would be equal to 2 times of P1. Hence P0. Hence option A is the correct answer. A vessel is filled with a gas at a pressure of 76 centimeter of mercury of a certain temperature. The mass of the gas is increased by 50% by introducing more gas in the vessel at the same temperature. The resultant pressure of the gas is, the options given are 76 centimeters of mercury, 108 centimeter of mercury, 112 centimeters of mercury, and 114 centimeters of mercury. Now, the formula for pressure exerted by the gas can be given as 1 by 3 rho c square. In this, c is the RMS velocity and rho is the density. So this can be written as 1 by 3 times mass upon volume instead of rho, and c is can be written as root of 3 RT upon m. Now in this, as we know that the temperature has been kept constant, so T is constant, the volume is also constant, so therefore we can write pressure is proportional to M. So therefore P2 upon P1 is equals to M2 upon M1. So now this is the mass of the gas and not the molecular weight. So therefore P2 upon P1 is given as 76 and M2 is 50% extra. So let's say M1 plus 50% of M1 upon M1. So solving this, P2 is equals upon 76 is equals to 3 upon 2. So P2 would be 3 upon 2 times 76. So that comes out as 114 centimeters. Hence option D is the correct answer. At what temperature in the RMS velocity of hydrogen molecule equal to that of the oxygen molecule at 47 degrees Celsius? The options given are 10 Kelvin, 20 Kelvin, 30 Kelvin and 40 Kelvin. Now the formula for RMS is given as root of 3 RT upon M. M is the molecular weight of the gas. So now for oxygen it would be TO and MO, whereas for hydrogen the value would be 3 times RT of hydrogen upon molecular mass of hydrogen. So therefore, since RMS speed of oxygen and that of hydrogen should be equal, we would equate these two expressions. Therefore, 3 root of 3 RT naught upon M naught would be equal to root of 3 R T of hydrogen upon mass of hydrogen. So squaring both sides and cancelling this 3R term, so therefore we get TO upon MO is equals to T of hydrogen upon the molecular mass of hydrogen. So temperature of oxygen would come out as T of hydrogen times molecular mass of oxygen upon molecular mass of hydrogen. Now T of hydrogen is given as 4. We need to find out the T of hydrogen, pardon me. So T of hydrogen would be T of oxygen times mass of hydrogen upon molecular mass of oxygen. Now temperature for oxygen is given as 47 degrees Celsius. So to convert it into Kelvin, we get it as 320 Kelvin times molecular mass of hydrogen is 2 and molecular mass of oxygen is 32. So on solving this, we get the value as 20 Kelvin. Hence option B is the correct answer. The root mean square speed of smoke particles, each of mass 5 into 10 raised to minus 17 kg in their Brownian motion in air at NTP is, the options given are 3 into 10 raised to minus 2 meters per second, 1.5 into 10 raised to minus 2 meter per second, 3 into 10 raised to minus 3 meter per second, and 1.5 into 10 raised to minus 3 meters per second. Now, as we know, the kinetic energy can be given as half mass times the VRMS square. Also, kinetic energy can also be given as 3 by 2 times the Boltzmann's constant into the temperature. So equating these two expressions, we get half m VRMS squared is equals to 3 upon 2 kb into T. So therefore VRMS would be equals to root of 3 kb T upon the mass of the gas. So substituting these values, we get 3 times the value of kb. Boltzmann's constant is 1.38 into 10 raised to minus 23, and the normal temperature is 0 degrees Celsius or 273 Kelvin upon mass of gram. Mass of the particles is given as 5 into 10 raised to minus 17 kg. So solving this, we get the answer as 1.5 into 10 raised to minus 2 meters per second. Hence option B is the correct answer. The temperature of an ideal gas is increased from 27 degrees Celsius to 127 degrees Celsius. Then percentage increase VRMS is 37%, 11%, 33% and 15.5%. Now the value for VRMS is given as root of 3RT upon the molecular weight. Now in this, the value of R and M are constant. 3 is also a constant, so therefore VRMS can be said to be proportional to root of T. So now percentage increase is equals to the increase in the temperature upon the initial temperature times 100. So therefore percentage increase in RMS in VRMS would be equal to root of T2 minus root T1, that is the increase in the temperature upon initial temperature, that is root of T1 times 100. Since M and R are constants, so we need not write them. So that is root of, now 127 degrees Celsius is converted into Kelvin to get the value of 400 minus T1, which is given as 27 degrees Celsius in Kelvin, is 300 Kelvin upon root of 300 into 100. So this comes out as 20 minus 17.32 upon 17.32 times 100. So that is nothing but 15.5%. So the increase is 15.5%, hence option D is the correct answer. The ratio of molar heat capacities of a diatomic gas at constant pressure to that at constant volume is, the options given are 7 by 5, 3 by 2, 3 by 5 and 5 by 2. So now the molar specific heat at constant pressure Cp, the general equation is 1 plus F upon 2 times R, and Cv is equals to 1 by 2 times F into R, where F is the degrees of freedom. Now for a diatomic gas, F is equals to 5 since there are 5 degrees of freedom. So therefore the value of Cp comes around 1 plus 5 by 2 times R, which is nothing but 7 by 2 R. Similarly, Cv is equals to 5 by 2 R. So therefore now the ratio of Cp upon Cv is equals to 7 by 2 R upon 5 by 2 R. So this gets cancelled and therefore the ratio of Cp upon Cv is 7 upon 5. Hence option A is the correct answer. A gaseous mixture enclosed in a vessel contains 1 gram mole of a gas A, gamma is given as 5 by 3, and another gas B with gamma equals 7 by 5 at a temperature T. The gases A and B do not react with each other and assumed to be ideal. The number of gram molecules of B, if gamma for the gaseous mixture is 9 by 13, is, the options given are 4 by 4, 12, 16 and 8. Now let the mixture have n number of gram molecules of gas B. Okay, and as we know, Cp minus Cv is equals to R, and Cp upon Cv is equals to gamma. So therefore by rearranging these two equations, we get Cv is equals to R upon gamma raised to minus 1. So using this relation for gas A, we get Cv for A as R upon 5 by 3 minus 1. So that would become 3 upon 2 times R. Similarly, for gas B, we get the value of Cv as R upon 7 by 2 minus 1. Here R upon gamma raised to minus 1, the whole thing raised to minus 1. This would be the expression. So this now comes out as 5 by 2 times R. And now for the entire mixture, CV is equals to R upon 19 by 13 minus 1. So this is 13 upon 6. 13 upon 6 times R. So this relation is modified as R upon gamma minus 1. So this comes as, so these are the values of CV for the gas A, gas B and the mixture. Now by conservation of energy, so therefore the molar specific heat of the mixture, that is CV for the mixture, can be given as uh, the number of gram moles of A times CV for A plus number of gram moles of B times CV for B upon number of gram moles of A plus number of gram moles of B. So now this CV for the mixture is 13 upon 6 times R, which is equals to the number of gram moles of A is 1 times 3 upon 2R plus the number of gram moles for B that we need to find out into 5 upon 2 times R upon 1 plus N. So therefore this is equals to 3 plus 5N times R upon 2 times 1 plus N. This is equals to 13 by 6 times R. Now in order to find out the value of N, we get the value of N as 2. Hence option A is the correct answer. If Cp and Cv denote the specific heats of unit mass of nitrogen at constant pressure and constant volume respectively, then the options given are Cp minus Cv is equals to R by 28, Cp minus Cv is equals to R by 7, Cp minus Cv is equals to R by 14 and Cp minus Cv is equals to R. Now using the Mayer's equation, for Mayer's equation for 1 mole, so Cp minus Cv is equals to R. So this equation is for 1 mole. So therefore for unit mass, we need the value of Cp minus Cv would be R divided by the molecular mass of the gas. So therefore Cp minus Cv for per unit mass would be R upon the molecular weight of nitrogen, since it exists in the diatomic form, would be 28. So Cp minus Cv is equals to R by 28. Hence option A is the correct answer. Half mole of helium is contained in a container at STP. How much heat energy is needed to double the pressure of the gas? Heat capacity of the gas is 3 joules per gram per Kelvin. The options given are 1436 joules, 736 joules, 1638 joules and 5698 joules. Now the amount of heat needed Q is NCV into delta T. Now this is the total heat capacity. So in order to find out CV, we need the molecular mass times the specific heat capacity CV. So that is 4, that molecular mass of helium is 4 and CV is given as 3. So the total specific heat CV would be 12 per mole per Kelvin. Now also, since the volume of the container isn't changed, so for constant volume, pressure is proportional to T. So therefore, P2 upon P1 is equals to T2 upon T1. And since the temperature is how much heat energy is to double the pressure, since the pressure is doubled, so P2 upon P1 can be written as 2. So therefore, T2 is equals to 2 times T1. Now here we need delta T. So delta T is nothing but T2 minus T1. So that is 2 times T1 minus T1, which is T1, and the value of T1 at STP would be 273 Kelvin. Now therefore, substituting all these values in this formula, so Q is equals to N is given as half mole, so half, value of Cv is 12, and the value of delta T is 273. So solving this we get 1638 joules, hence option C is the correct answer. 1 mole of an ideal monoatomic gas at temperature T0 expands slowly according to the law P upon V is equals to constant. If the final temperature is 2 times T0 supplied to the gas is the heat supplied to the gas is 2 times RTO 3 upon 2 RT0 and half of RT0. Now since they have given that the gas expands according to the relation P upon V is equals to constant, so we can write P upon V raised to minus 1 is equals to constant. Also, for any process which follows PV raised to X is equals to constant, the molar heat capacity C is given as R upon gamma minus 1 plus R upon 1 minus X. So this is a general formula, and from this, if we equate these two relations, we get the value of X as minus 1. And for ideal monoatomic gas, for a monoatomic gas, gamma is equals to 5 by 3. So therefore, substituting the value of gamma and X in this, so we get the molar heat capacity as C is equals to R upon 5 by 3 minus 1 plus R upon 1 minus 1. So this value comes out as 2 times R. So the heat supplied Q is equals to N C delta T. So that is equals to 1 mole. C is 2R and delta T is change in temperature, that is 2 T naught minus T naught. So that is equals to 2 times R into T naught. Hence option A is the correct answer. A gas mixture consists of 2 moles of oxygen and 4 moles of argon at temperature T. Neglecting all vibrational modes, the total internal energy of the system is, the options given are 4 RT, 9 RT, 11 RT and 15 RT. Now, the general formula for internal energy is F upon 2 nRT, where F is the degrees of freedom. Now, for oxygen, since oxygen is a diatomic molecule, F is 5. So therefore, U for oxygen is 5 upon 2 into the number of moles is 2 times RT. So that is 5 RT. Now, argon, similarly for argon, since it is a monoatomic gas, so therefore F would be 3. So internal energy for argon is 3 upon 2 into 4 moles of RT. So this value is 6 RT. So total internal energy is U of oxygen plus U of argon, that is 5 RT plus 6 RT, that is equals to 11 RT. Hence option C is the correct answer. If for a gas R upon Cv is equals to 0.67, this gas is made up of molecules which are, the options given are monoatomic, diatomic, polyatomic, and mixture of diatomic and polyatomic molecules. Now, for a gas, we know that R upon Cv is equals to gamma minus 1. However, the value of R upon Cv is given as 0.67. So therefore, gamma minus 1 can be equated to 0.67. So from this, the value of gamma we get as 0.67 plus 1, that is 1.67. This value of gamma as 1.67 is standard for monoatomic molecules. Hence, the molecules should be monoatomic. Hence, option A is the correct answer.